All right, let's talk about acetals, imines, and enamines. The goals of this lesson are to be able to predict the products of reactions involving acetals, imines, and enamines, and then also mechanisms for their formation and for their destruction, aka hydrolysis. We'll also look at a related reaction called reductive amination and learn its mechanism as well. And then we'll practice some synthesis of amines. We're probably going to do that in a different video. All right, so we're going to get started by making sure we have a common vocabulary around these functional groups. So pause and draw a generic representation of each of these groups. You should have something that looks like this. No cheating. So we have the hydrate. I wanted to kind of point something out. Hydrate, it's called the hydrate because we've added water to carbonyl compound. Hemiacetal, hemi means half. So here, look at the full acetal. You have two that look like ethers, but you have two alkoxy groups bonded to the same carbon. And this has come from a carbonyl, right? You have two bonds between carbon and oxygen. And two bonds between carbon and oxygen. It's just two different oxygens in the acetal. So the hemiacetal is half of that, right? You have one alkoxy and one hydroxyl looking group. Okay, so it's called a half acetal, hemiacetal. Aldehydes, ketones, imines, these should all be familiar. An imine kind of looks like a carbonyl, right? It has two bonds between the carbonyl, carbon, and nitrogen. In fact, you can make imines from aldehydes and ketones. They have the same oxidation state. Enamine should look to you like an enol or an alkylated enol. And then primary amines and secondary amines, these look to you like alcohols, but the one difference here is that when we refer to primary and secondary amines, we're actually referring to the number of alkyl groups on nitrogen, and that's a little bit different than what you're used to. So when we discussed alcohols, the only option is one alkyl group on an alcohol, right? That's the definition. So secondary alcohol, we're talking about the carbon bonded to the hydroxyl. And so that's different. For amines, you're talking about actually the number of alkyl groups, because you can even have, as you know, a tertiary amine with 3 alkyl groups on nitrogen. Turns out this one's not super relevant today. Secondary and primary amines are. All right, so make sure you have this common nomenclature down before you move on. Because a hydrate looks a lot like an acetal, except instead of hydroxyls, there are alkoxy groups on the acetal, we're going to really quickly review hydrate formation. So hydrates can be formed when aldehydes or ketones are in aqueous or basic conditions. So in acidic conditions, as you know, the first thing you do is protonate something. And I'm just jumping right ahead, but you know it's a great idea if you're learning this for the first time that you should just pause and try it yourself first. So in acid, we're going to protonate something. We have here a protonated aldehyde, and it is a really strong electrophile. Okay, so it's a super electrophile, strong electrophile. You can rationalize this in that now this resonance structure that puts a positive formal charge on carbon, it's still a minor resonance structure because carbon has an incomplete octet, but it definitely contributes more. So the protonated aldehyde is a really good electrophile. Water is going to attack. It's going to act as a nucleophile and attack. So here's our nucleophilic addition step. That gets us almost to the hydrate. I can mention that, water is a weak nucleophile, but it still attacks the carbonyl carbon because of this positive charge. And then now finally, you just need one more proton transfer step to get the hydrate. And as you've learned, hydrate formation is an equilibrium, and in fact, in most cases, the equilibrium constant is less than 1, so it favors the reactants. Okay. We can quickly review hemiacetal formation. So under basic conditions, and this is specifically basic conditions this time, so let's put in, this is basic conditions, this is the only time you can isolate the hemiacetal. It'll be formed under acidic conditions, but you're going to see in a minute that you can't isolate it. So under basic conditions, this time, so we have a base, contrast that to having an acid. We're going to attack. So the aldehyde is an electrophile. It was more electrophilic when we protonated it here, but it's still an electrophile even in the neutral state. And when you have this more reactive species, this alkoxide, it will go ahead and act as an electrophile right away. So we have nucleophilic addition, and this is a reversible step. And then now from here, there's really two things that can happen. One is that you can just reverse. So collapse, reform the strong CO double bond, and expel the methoxide, go backwards. That certainly happens. But you've been asked to draw the formation of the hemiacetal, and that also happens. So the second way to relieve that stress, that negative charge on oxygen, is simply to protonate it. And the proton source is just the conjugate acid of methoxide, methanol, which is the solvent here. Okay, so again, for the hemiacetal formation, the equilibrium constant is usually also less than 1. Except, of course, in the case of the cyclic hemiacetal, in which the equilibrium constant is greater than 1. Okay, so the cyclic hemiacetal, and as I've mentioned, we're going to talk about this a lot towards the end of the class. So you should pause and see if you can draw this mechanism. You're in base, we're going to deprotonate. That will generate an alkoxide. And in the same molecule, we have the aldehyde. So we attack. You're given the product, but it's always a good idea to double check and make sure you're forming the ring size that you expect. And this would make a 5-membered ring. Okay, and one last step to get to the product, we need to protonate. Our proton source in basic solution is water. Right now in hemiacetals, under basic conditions, we're stuck at the hemiacetal. There's nothing else that can happen. So, you can form the hemiacetal, or the hemiacetal can go ahead and reverse. So for fun, let's show the retro. So the reverse of hemiacetal formation. So in reverse, we're going to deprotonate. And then look at what we're doing. We need to collapse, reform the carbonyl. So collapse, expel methoxide. No, methoxide is not a great leaving group. However, you are forming the strong CO double bond. So in basic conditions, this is really it. Under acidic conditions, there's going to be a different story. Before we move on to looking at what happens when you treat an aldehyde or a ketone with an alcohol in acidic conditions, let's just take a minute and reflect on the differences between acidic and basic conditions in the context of nucleophilic additions to aldehydes and ketones. So pause and consider that on your own. So under aqueous acidic conditions, you're going to have hydronium act as a proton source and protonate something, and water will be the base or the nucleophile, depending on what's going on. In basic conditions, this time as the proton source, you're going to have water, and hydroxide will act as a base or a nucleophile. What will happen to the carbonyl first in acidic conditions? Well, you're going to protonate it. In acidic conditions, you're going to protonate the carbonyl using the proton source, which is hydronium. Then some weak nucleophile, water, or something else can attack. In basic conditions, what happens to the carbonyl first? It gets attacked by a nucleophile, usually a strong nucleophile. So strong nucleophile. Now we're going to have the alkoxide. What happens to it? Well, it gets protonated by the proton source, which, as we just discussed in base, is water. What happens to hydroxyl-like species in acidic conditions? Well, they can be protonated. Okay, so we can imagine we can protonate them. What have we done if we protonate that? Oh, interesting. We made water. Water's a good leaving group. How do I know? I know because it's the stable conjugate base of a strong acid. What happens to hydroxyl in aqueous basic conditions? So the scenario right here. Well, it could be deprotonated. And that would generate an alkoxide. And this can do one of two things. It can just become reprotonated by water. Or it could collapse and expel the nucleophile and go back to the ketone or aldehyde it was when we started, right here. All right, but I'm never going to lose that oxygen, right? That oxygen just kind of stuck with it. But under acidic conditions, I've made a good leaving group. Eureka. Okay, let's move on from here. So under acidic conditions, where we have some catalytic amount of acid, so this could be tosic acid, it could be triflic acid, it could be sulfuric acid, just some source of acid, we can observe formation of an acetal from aldehyde, or this also works with ketones. Let's take a look at what's going on here. So we can see here are the carbons from the aldehyde. And then what have we done? We've made some carbon-oxygen bonds. This is the aldehyde carbonyl carbon. Where did those methoxys come from? Well, they came from methanol. So you should pause and see if you can draw this mechanism first. Under acidic conditions, you're going to protonate something, where the something is the aldehyde, and the proton source will be protonated methanol. So whatever your acid is, it's going to first protonate the solvent. And then the protonated solvent is going to act to protonate the aldehyde. So our first step is a proton transfer reaction, and we generate the protonated aldehyde. We can go ahead and abbreviate the aromatic ring as phenyl. As you know, the protonated aldehyde is a super electrophile. And now the weak nucleophile methanol can attack it. Even if we don't put 2 and 2 together in on that, we can take a look at the product and see that clearly methanol makes a bond to the carbonyl carbon. That's going to happen now. So the lone pair from methanol is donated to the carbonyl. This will make an intermediate that looks a lot like a hemiacetal. It's a protonated hemiacetal. The stress on this intermediate is certainly the proton on the methoxy group. And you can see that that is also not in the product. So go ahead and deprotonate that. You'll use methanol as your source, as a base here. So methanol is going to act as the base and the nucleophile. And then protonated methanol is going to act as an acid. And you should make an analogy here to aqueous acidic conditions, even though this is acidic alcoholic conditions. So now after that proton transfer step, we do have a hemiacetal. However, we're under acidic conditions. So unlike in basic conditions, when the only thing to do for the hemiacetal is to deprotonate and go backwards, Under acidic conditions, we can protonate the hemiacetal. And again, even if you're not able to rationalize that, you can look at the product and clearly see that water is gone, or this hydroxyl rather is gone. It is not in the product. And to make the hydroxyl leave, you know that you need to make it water, make it a good leaving group, except in very specific contexts where you can make it leave as hydroxide. This is not one of those times. All right, now you generated water. Water is a good leaving group. Water leaves. At the same time that water is leaving, though, this lone pair on the methoxy kind of pushes it off. I like to call this the lone pair push. How do you know that happens? Well, if you show that lone pair pushing, you're going to get directly to the most stable resonance structure of this molecule. And then also you're forming a strong CO double bond, so it seems to make sense. Just a quick aside, your textbook works through this resonance structure, and this is perfectly fine. You can work through this resonance structure for now, but eventually I would like for you to show the lone pair push and get directly to the major resonance structure. From this major resonance structure, we are almost there. The stress on this molecule is the positive charge on oxygen, which is being shared with carbon. And so what do? It's a really good electrophile. We are going to attack with methanol. Methanol is the nucleophile here. It might be a weak nucleophile, but this is called an oxocarbenium ion. It is a strong electrophile. All right, there's a bit of trivia for you. Oxocarbenium ion. Now we are almost to our product. We're going to squeeze it in really small over here. All we have left is a proton transfer step to get to the final product. All right, we're almost there. So we need to deprotonate. We're going to go ahead and use methanol as our base and deprotonate, and we have the final acetal. All right, pause and kind of drink all this in or listen to the mechanism again. Oh, I'll just maybe show you the key here, right? So at the hemiacetal state, as we predicted in our little initial analysis, under acidic conditions, you can generate water, and water is a good leaving group. And we saw it leave here. And it did leave here. Okay, it was assisted by the lone pair push, LPP. And then from there, the oxocarbenium ion could be attacked by another molecule of methanol to generate the acetal. All right, so in the previous example, we had an aldehyde. We treated it with some alcohol under acidic conditions, and we generated the acetal. Now, one little twist on this is that if you treat it with a diol, and this specific diol is an old friend of yours, that's ethylene glycol. You've encountered it before. If you treat it with a diol, you can make this cyclic acetal. Okay, so here's the alcohol. It's been, deprotonated. So you should pause and see if you can draw the mechanism for this reaction. It's exactly like the previous example, except now you have a diol. So you have an intramolecular attack at some point. All right, the first step in acid is that you're going to protonate something. So we're going to protonate the carbonyl. We're going to do that with protonated ethylene glycol because that will ultimately be the acid. All right, from here we're going to generate the protonated aldehyde, which is a strong electrophile. Now our strong electrophile is going to be attacked by a nucleophile. The nucleophile in solution is the ethylene glycol. Now, ethylene glycol might be a weak nucleophile, but it is nucleophilic enough to attack that protonated aldehyde. From here, we have this weird protonated hemiacetal. You can tell the stress on this is the positive charge on oxygen, and it's going to be deprotonated. It's going to be deprotonated by another solvent molecule, so the neutral solvent molecule, to get your hemiacetal. Now, if you just kind of look at the product, if you forget the mechanism or you just kind of want to look at what's going on, you can see this hydroxyl is gone. It is no longer in the product. How do we make hydroxyls leave? We turn them into water. So again, we're going to use the protonated solvent as our acid. That's going to generate this protonated hemiacetal, but this time water is protonated and we have made a good leaving group. So from here, water is going to leave, but again, it doesn't exactly happen by itself. This lone pair on oxygen pushes it off, right? This is the lone pair push. We do this for two reasons. One, because it reminds us that forming this strong CO double bond is a driving force for this step, but also we like to draw the major resonance form of this intermediate. From here, we have a pretty strong electrophile, right? This is that oxocarbenium ion. It is electrophilic at carbon, as you can rationalize by the minor resonance form. Luckily for the molecule, it has a nucleophile in the same molecule, so that oxygen can come and attack carbon. So that's the intramolecular step that makes this a challenging mechanism oftentimes for us. Okay, so now we're almost there. We're going to have our protonated acetal. And now I'm drawing this really quickly. You know, if you're confused, you can number the atoms. You can make sure you don't lose any carbons. I'm just going to number atoms here. So 1, 2, 3, 4, 5. When I make a ring, I like to number between the two atoms making the new bond, so you can see everything looks good. So we have our protonated acetal. We're almost there. Just go ahead and take this solvent and deprotonate it. And we're there. We have our cyclic acetal. Okay, I want to take a time out here and think about what species each of these acetals were made from. So we're going to take this stepwise. The first thing you want to do is identify the acetal carbon. So pause and identify the acetal carbon for each of these species. The acetal carbon is the one that's bonded to two oxygens. So here we go. Why is that important? Well, the acetal carbon, that was a carbonyl carbon, right? So acetal carbons have 2 bonds to oxygen. Carbonyl carbons have 2 bonds to oxygen. And there's absolutely no redox chemistry going on here. There's no reducing agents or oxidizing agents. So we know that the acetal carbon must be the carbonyl carbon. Okay, now from here you want to break the acetal bonds. We're thinking retrosynthetically. And that's going to give you the alcohols and then your carbonyl species. So I'll do the easy one. Or the easier one. None of it's easy. So I'm going to go ahead and show you what I mean. So we're going to break the bonds between oxygen and the carbonyl carbon. These are going to become alcohols. And then the pink and now starred carbon, that was a carbonyl. If you want to try, go ahead and pause it and try. All right, so this was the carbonyl carbon, the pink carbon, and then we had 2 alcohols, so 2 molecules of ethanol. Okay, so there we go. If we wanted to make this acetal from these species, we would just treat it with acid. So let's say triflic acid or tosic acid or sulfuric acid, just some acid. Same deal. It gets a little bit harder now when you see you have this cyclic acetal. And so when you have the cyclic acetal, you're going to have a diol and a carbonyl compound. So pause and go through the same steps. Break these bonds. The pink carbon is going to be a carbonyl carbon. And then you have the alcohols, but this time you have this diol. You have ethylene glycol. Okay. The hardest one is the last one, right? That actually looks like it looks crazy. But now as fully intramolecular. So the carbonyl and the alcohols are all going to be part of the same molecule. You're going to not be deterred. Do the same thing. Break the acetal bonds. Draw the carbonyl there. And then this time we're going to be a little bit careful. We're going to figure out how many carbons we have. All right, 2 carbons to the oxygen. So 1, 2. 1, 2. All right, and we're good to go. So we're going to switch gears here. So acetals, let's kind of skip down, do a little summary here. So acetals, they are going to be made from an aldehyde or a ketone treating with some sort of acid, so tosic, triflic, sulfuric, in the presence of some alcohol. Okay, now this is reversible. We'll talk about that in a little bit. You can go backwards. Talk about that in a bit. Maybe you want to think about the diol makes that cyclic acetal, so maybe you want to think about that. Then we have the fully intermolecular variant. Whatever notes you need to put here are fine. We're going to change gears a little bit. It probably feels like we're changing gears a lot, but these mechanisms and these functional groups are very related to one another. We're going to take a look now, and if we take an aldehyde and we treat it specifically with the primary amine, we're going to form what's called an imine. So an imine has this carbon-nitrogen double bond. It looks a lot like the carbon-oxygen double bond. Because you have nitrogen and it makes 3 bonds, you also have this alkyl group on the nitrogen, whereas you don't have anything on the oxygen of an aldehyde or a ketone. Again, there is no redox chemistry happening, right? We have 2 bonds between carbon and oxygen here. 1, 2. 2 bonds between carbon and nitrogen in the imine. 1, 2. So there's no redox chemistry going on here. All right. So last thing, we have this why is the pH 5 question. We'll talk about that. pH 5 is actually really important for this reaction to run at a reasonable rate. And in your textbook, it may call these conditions mildly acidic. Okay, we'll answer the rest of the questions later. So now we're going to try to draw a complete curved arrow mechanism for this transformation. Now you might be tempted in mildly acidic conditions to protonate something, but it turns out that the amine is quite nucleophilic, and what actually happens first is that the amine attacks just the carbonyl. So we do not protonate the carbonyl first, the amine can just attack it. This generates an interesting intermediate. Okay, we have a negative formal charge on oxygen and a positive formal charge on nitrogen. This might make you feel a little bit uncomfortable, but I can assure you this mechanism has been studied quite a bit, and we have lots of evidence that suggests it's correct and the species does exist. What you want to do from here is what you may expect. You're going to want to deprotonate that amine. So next we're going to deprotonate the amine, and we can do so, go ahead and we can just use the amine from the solution to do that as our base. Let's go ahead and write that down. So this is acting as a base. Our intermediate here is acting as an acid. Now, from this intermediate, I want you to consider what's going to happen next. So take a look at the product and think what needs to happen to form that product. And if you thought that this water, or this oxygen rather, gave it away. If you thought that this oxygen needs to leave, you're absolutely correct. It does need to leave, but it's going to leave as water. So the next step is that we're going to protonate that oxygen. Now, what is the acid source? You can use the protonated amine as the acid source. We actually just generated this, right here. So we can use that as the acid source. So go ahead and protonate the oxygen. I'm going to start abbreviating the aromatic ring as phenyl to make our lives a little bit easier. Okay. Now from here we're going to protonate one more time. You can use the protonated amine again if you like. And it turns out that this last step, this is actually the rate determining step of this entire reaction, and it's why that this reaction has to be specifically pH 5 or mildly acidic. It needs to be acidic enough to protonate this oxygen, but not so acidic that all of your amine is protonated, right? I mean, amines are basic. So it needs to be acidic enough to where you do make water, you do make that leaving group, but you still have some unprotonated amine to act as a nucleophile on this first step, and it's a delicate balance. All right, so right now we have generated water. Water is a leaving group. So water can leave, but again, that doesn't happen really on its own. It happens with this lone pair push, reforming a strong carbon-nitrogen double bond. And now we're almost there. You can see that we are one deprotonation away from making the imines. We have a protonated imine. And if you want, you can use water. If you don't want, we can use the neutral amine. That's probably better. Let's use the neutral amine. And we're going to deprotonate and form the imine product. All these steps are reversible, so just to let you know, if you were in lab, you would use a piece of glassware that would allow you to remove the water. And when you remove the product of this last reaction, by Le Chatelier's principles, that drives all of these other equilibria, so you can form the imine. Okay, so in the process of drawing that mechanism, we did address how the protonation states are different than in acetal formation. But again, the big difference is that you attacked the neutral aldehyde, and you did that because amines are quite nucleophilic. And then that required this kind of weird protonation steps, and that's why we have pH 5. So we can go ahead and make water a good leaving group and form the imine. Now, enamine formation. How do we form an enamine? I want you to take a look at this and compare and contrast with imine formation. So go ahead and pause. All right, this time I've drawn a ketone instead of an aldehyde, but that is not the big difference. The big difference here is the secondary amine. And so because we have the secondary amine, we're going to see an enamine. When you have a primary amine, highlighted in pink here, you're going to have an imine formed. So I have a ketone. This also works with aldehyde, so I'll go ahead and write or aldehyde. Again, we have the mildly acidic conditions. So mildly acidic, and this is our enamine. And you might say, hey, this enamine, it only has one bond between carbon and nitrogen. Did you do some redox chemistry? No, we didn't. You want to think about the enamine like an enol, and you know that enols come from carbonyls. So you can think about an enamine as being related to an imine. But if you have a secondary amine that you made it from, like in this case, it's actually going to be related to an iminium. You can never get this positive charge off of nitrogen unless you make the enamine, which comes from deprotonating alpha to it. Okay, that was a lot of information. Let's just take a little pause and try this mechanism. The beginning of this mechanism is exactly like imine formation. So you should probably pause and try it yourself. Wow, I've said that a lot during this video, but it's true. You should always be trying these things yourself, especially when you're learning them for the first time or practicing them before a test. So we have our ketone. Our ketone is going to act as the electrophile. Previously, under acidic conditions, we've protonated it, but amines are good enough nucleophiles that they actually just attack the neutral carbonyl. That will generate this intermediate that has a negative formal charge on oxygen and a positive formal charge on the nitrogen of the amine. The first thing that we're going to do is deprotonate that amine just like we did before. If we need a base, we're going to use the neutral amine from the solution. So we have a proton transfer step, which follows our nucleophilic addition step. From here, we have just the negative formal charge on oxygen, and keeping in mind that we want oxygen to leave as water, we're going to go ahead and use our newly generated acid to protonate that oxygen. That's going to generate for us this neutral intermediate. Looks pretty stable, right? Yeah, I mean it is, but we're under mildly acidic conditions, so we can go ahead and protonate it to generate water. Once you've generated water, which we're almost there, so once we've generated the water, then the water can leave. And if you're in a lab, you would be using a really special piece of glassware to collect that water and take it away and use Le Chatelier's principle to drive the reaction. All right, so now we've generated water. We're going to make it leave. So lone pair push, water leaves. That generates this intermediate. Now I gave this intermediate a name earlier. I called it an iminium ion. It looks like an imine because it has two bonds between carbon and nitrogen, but it also has that positive formal charge on nitrogen. Now this intermediate is extremely similar to the protonated amine. I'm going to put a little box around it here. So the protonated imine, technically also an iminium. So the protonated imine looks exactly like this iminium species. Now, for imine formation, sorry, I'm going to switch back up to this slide. We could just deprotonate and that relieved the positive charge on nitrogen and we were all good. And that's because we started with a primary amine. But this time, we started with the secondary amine. And there are no protons here, at least not directly on nitrogen. So the only way to relieve that positive formal charge on nitrogen is actually to deprotonate one of the alpha carbons. And of course, you would deprotonate whatever alpha carbon gave you the most substituted double bond here. Luckily, those alpha carbons are exactly the same, so we don't have to worry about that, thank goodness. Okay, so we're deprotonating. This looks a lot like making an enol under acidic conditions. And that gets us directly to our enamine product. Okay. All right, pause and digest that. Even better yet, summarize those two reactions. All right, hopefully you came up with something like this. We're under acidic conditions. The oxygen of the aldehyde or ketone is totally replaced with something new. So when you have an alcohol, it's replaced with two of those to become an acetal. When you have a primary amine, you get an imine. When you have a secondary amine, you get an enamine because you have to deprotonate in order to relieve the positive charge on nitrogen like we just discussed. And you might also add the review reactions we discussed at the beginning to set the stage. So moving on from here, I mentioned that all of these steps, all these reactions are reversible. So we're going to go ahead and look at the hydrolysis reaction. So the reverse of all of these formation reactions. Oh, and you guys should try this on your own. All right. So nucleophilic additions to form acetals, imines, and enamines, these are all reversible. We're going to draw the complete curved arrow mechanism for the decomposition of each of these functional groups to the aldehyde or ketone starting material. And I want to make a really important point here, which is that the lowest energy pathway for the decomposition, it is the exact opposite of the formation, as long as you're under the same conditions which you are here. All right, so we're going to look for acetal going to the aldehyde or ketone. Again, I do suggest that you pause and try this. It is the exact reverse of this way. So we're in acid. The first thing we're going to do is protonate something. Since we're in aqueous acid, we're going to use hydronium to do that, consistent with our discussion at the beginning of class. Now we generated a protonated acetal. Just like when we generate water, we generated methanol here, and this is going to be a good leaving group. So this is going to be a good leaving group. So we're going to go ahead and have it leave. Again, it doesn't exactly leave entirely on its own. It gets a little push from that lone pair, because when that lone pair pushes it off, we get directly to the major resonance structure of this intermediate. We also show a strong CO pi bond being formed. We've expelled methanol and generated the oxocarbenium ion, which is a really good electrophile. So remembering what's happening here, we're reforming the aldehyde. That oxygen is going to come from water. So our next step here is to go ahead and make a bond between the oxygen of water and the oxocarbenium ion. Water acts as a nucleophile, attacking that electrophile. If you compare to the acetal formation mechanism, this is the exact reverse. All right, so now we have that oxygen of our aldehyde. So looking at the product, you can see that this methoxy needs to leave. It's going to leave as methanol. Before we can generate methanol here, we're going to deprotonate this intermediate, the protonated hemiacetal. So we deprotonate the protonated hemiacetal, and then we're going to protonate methanol to make it go away, or to make it a good leaving group. So our source of protons is hydronium. Okay, we're getting close here. So now we've generated protonated methanol, or we've generated methanol, which is our good leaving group. Same deal as before. The lone pair is going to push off the good leaving group, reform the strong CO double bond, and we are simply one protonation step away. So we can use the methanol we just expelled to deprotonate. Or we could have used water to deprotonate and generate the aldehyde. So this mechanism is the exact reverse of acetal formation. You can check it. So we've just seen that if we take an acetal and treat it with acid in the presence of water, we can regenerate the aldehyde. But acetals are stable to base. So under basic conditions, acetals are stable. So why is that? Well, what do bases do? Or what does hydroxide do? Okay, well, it connect as a base. Well, there are no acidic protons in the acetal. Or it could act as a nucleophile, but I mean, it's certainly not, so not going to do an SN2 here. No, 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 no. So there's just nothing, no reactivity that's possible. Okay, do we care? Yes. That if for some reason we needed to treat the rest of the molecule with base or a strong nucleophile, we could do that, and the acetal would not be affected. So So we're going to see the consequences of this when we talk about synthesis again. All right, now we're going to look at the hydrolysis of an imine. So we have an imine, and we're going to treat it with aqueous acid. And we're going to create the aldehyde and primary amines, where the primary amine is here. And then the carbons from the aldehyde were here. Okay, where does that oxygen come from? It comes from water. So again, I wanted to point out that the hydrolysis is the exact opposite of the formation. So let's try. So the first thing we're going to do is protonate the amine, and we're going to use hydronium as the acid. So we're going to protonate the imine. That will generate an iminium ion. Iminium ions are quite strong electrophiles, just like oxocarbenium ions are strong electrophiles. So water is going to attack it. It's going to act as a nucleophile. How do I know? Well, I just rationalized it for you, but if we lose track of that, just understand that's where the oxygen is coming from in the aldehyde. It's coming from water. This generates an intermediate that looks like this. And you should go and compare this to imine formation because the mechanism will look exactly the same. Okay. From here, the stress on this molecule is the positive charge on this intermediate, so we're going to deprotonate using water. We need to expel the amine. We're not going to do it right now because that would give us this species, which you know is not a good leaving group. That is not stable. It is the conjugate base of a weak acid. So we are not going to generate that. So in order to make a good leaving group, we're going to protonate the amine. And we can use hydronium to do this. And we're almost there. So if you look at the mechanism for imine formation, it formed via this intermediate. And because it formed via this intermediate, we're going to regenerate that because the reverse pathway is the exact opposite as the forward pathway. So how do I generate this O-? Well, we're going to need to deprotonate the oxygen here. Now you might say, okay, this is crazy. How can you deprotonate this alcohol with water? Well, understand that this is more acidic than you might expect because there is the positive charge in the molecule and because I'm telling you to do it. So those are your two reasons. All right, now from this intermediate, we're going to lone pair push off this good amine leaving group. Get the amine and you get the aldehyde. One more mechanism to go. We are almost there. This is the same introduction that I've had on every single one of these slides, which is that the hydrolysis will be the exact reverse as the formation. So the hydrolysis of an enamine gives us a ketone and a secondary amine. The first step of hydrolysis is going to be the final step of an enamine formation. The final step of enamine formation is deprotonation. So the first step of enamine hydrolysis or destruction is protonation. If you don't have the mechanism in front of you or in the back of your head like I do, you guys know, this. When you're in acid, you're probably going to protonate something. You learned one exception today, but in general, in acid, protonate. This gives us that iminium ion. Now, to form the enamine, we deprotonated alpha, but remember, we're not generating it, we're destroying it. So another possibility is that water adds to it. So it's electrophilic at carbon, water is a nucleophile, and water can add. And that will get us to this intermediate here that was formed on the pathway to forming the enamine. Okay, so this intermediate. Now, from here, keeping in mind that this oxygen from water is the oxygen in the ketone, we're going to go ahead and start to deprotonate it. So we're going to use water to do that. This should look really similar to the imine hydrolysis. From here, it's pretty much the same. We have to make a good leaving group out of this amine, so we need to protonate it, just like we would a hydroxyl. We're going to protonate it using hydronium. That will generate this intermediate, which has the protonated amine. You have your good leaving group now. We're almost there. First, just because, again, this mechanism is the exact reverse of the formation, we're going to form that same intermediate we had before. And then now we'll have our lone pair push, reform your strong carbonyl CO double bond, and expel your good leaving group, your amine. And that's it. We've hydrolyzed our enamine. What is there left to do here? Well, you can label all these steps as proton transfer, elimination, nucleophilic addition, and really think carefully about each of them. And then you should summarize these hydrolysis reactions.